Okay, sorry. So, welcome everyone. Welcome to this week's presentation. Today I'm going to present a paper called End-to-End Recovery of Human Shape and Pose. It's an older paper from 2018, and it's a very important paper in the field of digital humans. So, let's get started. So, the basic premise of the paper is I'm sure probably most of you are somewhat familiar with the field of pose estimation in general. So, where you basically take an image or a video. Can you guys hear me, by the way? I'm not hearing anything right now.
Yes, we can hear you.
Okay, nice. Where in pose estimation, you basically have an image or a video and you want to predict a skeleton onto the image to model the pose of the person. And if you look at this from a more general perspective, you can sort of say if you're modeling humans or human bodies in general, you have a spectrum of abstraction. So a very abstract model would be like a point model for a human or a bounding box, I guess, where you just have the position. And then a more complex model is a skeleton, which is sort of the standard situation for a general pose estimation. And then sort of the most complex thing that is in use generally at the moment is a human mesh model. So these are usually based on what's called SMPL, which is a type of model, which I will introduce you guys to in a moment. And what this paper basically does is it takes an image with a person and uses a machine learning pipeline to reconstruct a human mesh from the person. And this human mesh will model both the pose of the person, but also the body shape. So it's quite a challenging task. And this paper is specific also in the, or is interesting in the sense that it's not just this already kind of challenging task, it's also in real time. So it's a very efficient pipeline. And you can see here some examples where you have people and then the 3D model, the mesh that is reconstructed from the image. And you can see that these are quite complex and sometimes even work with some kind of occlusion, like here, for example, where a lot of information is basically inferred by the model and is not directly visible. Okay, so preliminary, this is very important. This is basically what this is based on. So this is a very famous paper. It's called SMPL, a skinned multi-person linear model. And this is basically, as I kind of said, the standard model for this kind of human mesh reconstruction or generally human meshes that are parametric. Of course, you can model a human like any other 3D object in like Blender or OpenGL or something like that, just using computer graphics. But if you have a parametric model, this is pretty much the standard from what I know. There are also a lot of variants of this model, but this is the basic model. Okay. So I'm going to give an introduction to this model. I'm not going to go into all of the details because it's a bit technical and I want to focus on the main paper basically. So basically the model is defined by a set of parameters and ingredients, so to say. So you have a skeleton with 23 joints. So this is what you have in a regular pose estimation model. Basically, you have some joints that are going to be in specific positions, key points of the body. And then you have a mesh that is on top of this skeleton with, in this case, n equal to 6,890 vertices. And this zero pose mesh, so there's basically a basic mesh of a generic human that is designed. And this will be a vector of 3 times n numbers. So you have for each vertex, you get xyz, right? And this will be in zero pose. And this basic mesh was actually designed by an artist. So this is sort of the starting point. And then you have a blend weight matrix, W here, which is an n times k matrix. And what this does is, k is the number of joints, right? So you get a weight for each joint and combined with each vertex. And this sort of dictates how much each joint will influence each vertex. So you can imagine that, for example, if you have the joint here, this will have a strong influence on all of the vertices around here. But for example, there's also a vertex point here, and the weight in the blend matrix of this with this will be very close to 0 or 0, because actually this joint does not influence this vertex point much. So this is the blend weight matrix. Then you have a blend shape function, which works in conjunction with a shape parameter, beta. So in general, you have sort of two parameters that define the model. You have the shape parameter, beta, which is a vector, and you have the pose parameter, theta. And the shape parameter basically defines the shape of the individual person. So like basically the body shape. And then the pose will define the pose that they're doing. So basically you can have one beta for one individual human. And then they can, of course, do many different poses. So what you do is you have a blend shape, yeah?
What's the dimension of those?
These betas,
Yeah.
so it says here just the the number of values, right? So this is,
I guess
well,
it's not important. It's just like you define it however.
yeah, you basically have to define this in your model. It will generally not be a super large number because it's sort of, you get it from a kind of PCA actually. So
Okay.
it will be like less than 20 components usually. I don't remember right now. You
Okay,
will
okay.
see in a moment. But you can sort of see these as just some parameters. They are not interpretable, right?
Yeah. That's what I figured. Okay. Thanks.
So you get a blend shape function where you take the parameters and you map them onto basically your vertices. So basically this will shape the human. So here's an example. You start out with just the zero pose with the weights, which, as I said, they define. So this joint, for example, will influence all of these vertices, but will not influence these, right? This is defined by the W. And then you add the shape function, beta, and this will change the shape. So basically they push some of the vertices further apart if the body shape is larger and stuff like that. Right. And then you have a joint regressor here, which again takes beta and now projects it onto the joints. So again, also the joints will also, of course, be influenced by the shape of the body. So this is what that does. So you can see here, you have T plus BS, and then you have the J for the skeleton. And then the next thing is the pose blend function. So it does a similar thing, but now for the pose. So basically here, you now have the zero pose, the shape, and then the pose. And you can see right now, nothing has changed really. The pose has not yet been executed. What you do now is you take a skinning function, it's called, which is this monstrosity here, which takes the T, the J, the theta, and the W, and then basically outputs the full posed mesh. And this skinning function, actually, I will not talk that much about it. If you're interested in it, you can read the paper. Basically, it's not invented by the paper. These kinds of function already existed. They use either a linear or dual quaternion function. Basically, what it does is you have a bunch of rotation matrices that basically do this pose shaping. So it's based on 3D geometry, as you can imagine. If you want to know more about the details, you can look into the paper. Okay. So
yeah,
yes.
yeah. I'm sorry. Can you like repeat the joint regressor one? I don't know.
The what?
I didn't understand the joint regressor one. I didn't understand the point.
Can you say it again? Sorry, I didn't catch it.
On the previous slide, the joint regressor. Yeah, this one.
The
The
joint
JT.
regressor. Oh, yeah. So this takes the shape parameters
Mhm.
and outputs the joint vector. So the positions of the joints, right? So of course the skeleton. So these white dots are the joints, right? Which basically define the skeleton. The skeleton will also depend on the body shape,
Yeah.
right? So the joints will change a little bit depending on the exact shape parameters. So that's what the
Okay.
joint regressor is for.
Okay. What about the I think you mentioned about the real-time reconstruction, right? The SMPL helps for real-time reconstruction.
Sorry, I cannot hear you that well right
Yeah,
now.
I think it's in the first slide, but you've mentioned about real-time reconstruction, I guess. But can you like
What do you mean?
which okay? I think somewhere in the slide you've mentioned about real-time construction. You were
Oh yeah,
saying
yeah.
that.
So this is okay. This is a preliminary, right? This is the
Okay.
model that they use for the actual paper. This is a different paper, right? That I'm talking about right now.
Yeah. Yeah.
So
Yeah.
I will talk about that later. You will see it then.
Okay.
But yeah, I mean, if you guys are,
Okay.
I hope you guys can follow this. It's a little bit technical, of course. There's a lot of
But
symbols.
but there are parameters at some point, right?
Yeah,
Mm,
yeah. You will see all that.
okay.
Okay.
Um,
Can you come back to the slide, Aaron? Sorry,
Which one?
this one. So I was trying to understand the beginning when you were talking about the skinning function. Can you please like repeat what is skinning function again?
So the skinning function basically is you take. You'll
Everything you
see some
have.
more details about this. You take everything. So
Okay.
you have this TP, which you construct like this, which is
Mm-hmm.
the sort of the basic positions of the mesh vertices. Then you plug this into the skinning function
Mm-hmm.
together with the pose, with the joint regressor and the theta and the W.
Mm-hmm.
And basically this will then execute the pose, right? So you have to combine for example, you have to combine the joints with the blend weight to determine how to actually change the mesh and stuff like that, right? You will see that in a moment, a little bit more in detail.
Okay. Okay.
Okay. So let me see. Okay, yeah. So this is
Okay,
next
maybe
slide.
one last thing. Can you go back to the notation
Yes,
one
of
last time?
course. Always, we have time.
To the notation back.
Oh yeah.
Okay, so W is n times k, and the output of the regressor is 3 times k.
Yes.
And then if you go back to the slide afterwards, they both define the second parameter of the model, right?
What do you mean?
So what I mean in A, you define the pose with T, which are the vertices, and W, which is the shape matrix. And the dimension of W is n times k.
Yes.
So joint time vertices. And then if you move on to B, and you look at the second parameter which replace it, which is G of beta, the shape, this is only 3 times k.
Yeah, but this is not okay. This is I understand what you mean. This is not really meant to be. It replaces this. I think it's just meant to be. We add this to the model. I don't think this is really. It's not meant to be that you take W and then you replace it with J. It's just in the end you will need all of these components, right? It's just that the joint.
Okay, so it's not like 2 parameters of a whole defined model.
No. I mean, of course, the joint regressor has 3k because for each joint you will need 3 numbers, right? And then for the blend weight matrix, you have n times k because you just want to define what is the weight between this joint and I don't know this vertex or something.
Okay.
Okay, sure. So some more details here. So I just want to show you a little bit some of the functions here. I'm not going to show the scanning function because it's a little bit more complicated, but it's not that bad. If you're actually interested, you can read the paper. We can look at it later if you want to. So the blend shape function is just basically the components of beta, and then you sum them, and you have this matrix here, which is basically comes from a PCA. So all of these models are learned, right? So you basically take a database of human meshes, which you get from motion capturing, and then you basically learn these, right, from this kind of linear expression. And then for the pose blending, you again have the PCA here, but now for the not for the shape displacements, but for the pose displacements. And these are rotation matrices. So this is basically not rotation matrices. These are functions which map from the theta to 9k. So 9 here, 3 by 3. It's a rotation matrix. So you get one rotation matrix for each joint. Then you have this rotational term basically. And then for the joint regressor, you basically just take the zero pose with the shape function, and you apply a linear operation, a matrix that you can also learn during the process, right? And in the in the standard setting, which is different from what we will look at now, in the original paper, they describe basically an algorithm how you can learn all of this from mesh data, basically. But I'm not going to cover that in depth because, again, first of all, it takes time, but also it's not the focus, because what we will look at now is how to actually learn it from images, right? Okay. I hope this was reasonably clear. You don't have to be rock solid on everything. It's can be a bit overwhelming at first, but I think you got the basic idea. You basically have a pretty in-depth model of how to shape the human body mesh, right? Okay. So let's go to the methodology. So how this works basically is you basically have two components. So you start with your image. You have a CNN backbone, right? A convolutional encoder. So this paper was from 2018, so it's not a transformer, obviously. And then you put this into an iterative regression, which I will talk about later. This is sort of ignore this at first. So you take this, you do something with it, and then you output from this encoding the shape parameter, the pose parameter, and then these camera parameters. So these two you already will know. These are from the SMPL, right? So you have basically, you want to predict from this image the shape of the person and the pose of the person, right? And then you also have to, of course, predict where the camera is, right? Because the projection on the 2D image will depend on where you look at it from. I think that's pretty obvious. So you will have basically the position of the camera, then how far it is away, and the rotation. So basically the angle from which it's looking at the person. Right. And then you you take this 3D model, and this in itself already kind of seems like it would work, right? You basically just predict this, and you do a projection of it. So you project this back into the image and get a projection loss. And then you just compare how much does it match up with the person. And it turns out actually that this does not work in a realistic setting because, and it makes sense actually, this is highly underdetermined, right? You can make a lot of nonsensical meshes basically that will map onto this 2D image. So let me see. I have some examples here from later. So if you just take basically only this part, you end up with these, they say monsters in the paper. So basically, if you look from this, it looks sort of reasonable, but if you actually look at the 3D model, it's not really a human body, right? So you sort of have to bias the model into producing parameters of theta and beta that actually make sense, that actually are similar to what human bodies look like, right? Because of course you can put whatever numbers you want in here and it will produce something, but it's in many cases not going to look like an actual human. So what they do is they train a discriminator which takes these parameters and then looks at a database of real data of like motion captured meshes and basically is trained in an adversarial sense. So it's like a gun kind of. I mean, it's not like a gun. It pretty much is a gun in a sense. You train it to tell whether it's a real human from here, right? Or if it's a human that was produced from this method, right? And you add this as an additional loss. So you basically do a kind of regularization where you bias your model into producing realistic human meshes that is learned. So that is basically the trick, I would say, of this paper, to do this, what they call adversarial prior. And there are a lot of tricks involved with this that we will also see in a moment.
Aaron, can I ask a question?
Of course.
So in the regression, you have a kind of a cyclic, how do you say, cyclic arrow?
Yeah, I will explain this in a bit.
Okay, and one question more. So what are S, R, and T camera parameters?
So, I mean, I'm not an expert on camera calibration, but I'm pretty sure T is the translation. So basically where the camera is positioned. Then R is the rotation. And S is the, how do you say it? Like the, it's a scalars, right? So you have to look at how much it scales. So basically how much the camera is zooming.
Okay, thank you.
So
So
I think
yeah.
I think like if I still didn't get the discriminator part, so I think they have the projection here at first to calculate the difference between the ones that's currently the one that we get from the pose and the shape, right? And so like we have a projection here, and then we are trying to calculate the loss of the image, of the 3D image, and the projected one, right? And why do we need a discriminator? Can we just use projection loss? I
So
didn't understand
you
that.
okay? So you have to understand. So you maybe I hope I understood you right. So we don't have any 3D labeled data a priori. You can add them. I will show you in a bit. But basically, in the most basic setting, you only have the image, right? So if you compare this 3D model with the image, you will just you project it onto the image, and then you compare this, right, to your label, which will be just a skeleton usually.
Yeah.
And this
Oh,
is
this
underdetermined.
So the
Yeah.
discriminator thing is for to hinder having monsters and real
Yeah, exactly. You basically want to bias the model, as I've said, to produce humans, not some kind of weird monsters that intersects
I see.
itself or has nonsensical. Like, and maybe I'm going to show this again. Like, for example, here, this is like basically it's looking in the wrong direction. The arms are like super weird and stuff. It's just because this, if you project it onto the human, it works, right? Basically, the model has just mushed this mesh into the human projection. But if you look at the 3D model, it does not make sense at all.
But
What it feels like to me, if I can add something maybe, is that so you're trying to infer a 3D position based on a 2D image. And the thing is, the set of possible beta and theta to do this is way too big.
Yes,
so you want to
exactly.
put constraints on the model, and the goal of the discriminator is basically to extract what these constraints look like from the data.
Yeah, it's well put. Exactly.
So
Because this is really, really underdetermined, right?
I
Basically
think
impossible.
if they just gave the direction to the vertices or the joints, the direction of the joints, they wouldn't have this problem. Or, for example, I see in the monsters, Aaron, if you go back to the monsters,
Yeah.
so some, especially in the second one, for example, the feet are reversed. The first one, sorry, the first one, the feet are reversed
Yeah.
in the reverse direction. I think one thing could be just instead of using a GAN, can be like just giving in direction information or direction parameter instead of like.
I'm not sure because you might. So the problem is you will also get stuck then in local optima, right? So this is basically a local optimum of the model.
Mm.
And if you don't constrain the model to not do this,
Yeah.
basically, you might just not find a model, an optimum
Yeah.
that actually works.
Why not?
Right?
Because in the monsters, the only problem seems like the direction of the joint. So the direction is here in the first one, for example, but it was supposed to be this direction. So you just give X, Y, Z parameters and it would maybe work. I don't know.
I'm not sure. I mean, there are probably other ways to do this, but I mean, the thing is, I think the problem in principle is that it's really undetermined in the direction of the image
Maybe
plane, right?
I can, like, if I
Yeah.
understood your point correctly, is that we already have biological limitations. So we already have sets of possible rotation matrices for these joints.
Yes.
And what he's saying, for instance, in the foot, it's totally 180 degrees, which is biologically impossible. And so would that work if we would just implement these at first? Because if you go back to the monsters,
So you're basically saying
yeah,
you do some kind
this
of
one, like for instance, yeah, the hip, you cannot rotate your hip
Right.
that much. Your feet cannot go like 180 degrees, stuff like this.
Yeah.
And
But actually, it can because in the second monster, for example, the whole direction is right hand side, but it was supposed to be left hand side.
no, but if you look at the elbow, for instance, you cannot turn your elbow like this.
Yeah, but for the feet, it's perfectly fine for the second one. Like if the direction of the legs are
Again, if you
The
look
first
like
one,
that,
you mean.
it's definitely something happened. But yeah, I mean, yeah, sure. I think so. Are you saying
That's perfectly
basically
fine.
what you could do is, of course, you can try to do some sort of handcrafted limitations on the
Yeah.
space, right? I mean, that would work in principle somehow, but the problem is, again, these are not interpretable parameters, right? So it's
To
not
me,
so
it
simple.
feels just like putting, I don't know, physical limitations on like physical estimating models. You just want to
Yeah.
prevent the states that are not possible of energy and stuff like this, and you just do the same with the range of motion of the joints.
Yeah, somehow, yes.
Like,
Yes.
yeah,
Aaron, you know what? I think I understood why they didn't put the direction information there.
Mm-hmm.
Because they don't have the ground truth of 3D.
Yeah, that's what I said, right?
Yeah.
There's,
Yeah.
I mean, you can include some 3D ground truth, but in
Yeah.
principle, you don't need it.
Yeah.
Exactly.
Okay,
Okay,
let me.
perfect.
I'm
Now
gonna
I
continue.
understand. Now I
Let me
understand. So
continue a bit.
GAN is a better solution. Okay.
You will
Yeah.
also see that this is not a gun in the. You don't have regular issues with gun for some reasons. I will explain. Okay. So this is basically this, right? This is the iterative 3D regression with feedback. It's called. So you have here. This is basically what you want to infer, right? So you have the theta, the beta, and then the camera parameters. So this is this. And basically you have a ResNet that takes in the image and puts out this theta. And then you do a projection. So this you have x here, which are the key points based on theta and beta. So this is basically the skeleton, which will be based on the SMPL model. You take this and then you do this projection operation. It will depend on the camera, right? And will produce the projection. So basically you just project. So if you take this, you would project it onto the image plane from the same angle as the photo was taken. So you take this projection and then you basically do they do an L1 loss in this case, right? So you just take a loss. And here this V is just, you need a flag to put to 0 if the joint is actually not visible in the image. Right? Okay. So the problem with this approach is that actually in practice it turns out that the model cannot produce these parameters in a good way in just one step, the ResNet, right? So what they actually do is they do an iterative prediction where basically you take multiple steps. So you produce one prediction and then you have the model do a correction multiple times. So it predicts this delta theta t, and you do this for 3 steps in the paper. So it's not a lot, but you basically do an iterative approach that you then compare with the reprojection loss, right? So this is why you have this error here. I mean, it's
Can you
a
repeat
it's not,
once again?
yeah. So, should I explain it again?
Yeah, like once again, please.
So they 1 second. So if you do the reconstruction directly, it's not going to be very accurate. So what you do is you take the module, which is it's actually not a ResNet. Wait. Okay, yeah, I should say it like this. You take a ResNet takes in the image and gives out an encoding. Wait, no, I went too far. So the ResNet takes, so this is an encoder, right? This is a ResNet. Gives you an image encoding, a vector, right?
Mhm.
And then this vector is taken by an MLP and produces a current estimate, right? A theta,
Mhm.
right? And then you basically do this 3 times, and you make the model produce a correction based on the current one, right?
Mhm.
And you train it to do that.
Okay.
Okay, yeah. I think it's not. I mean, I would say it's more a technical detail. Probably, I'm not sure if you could do this differently today with transformers. Maybe you can do it in 1 step now. Maybe even you could do it back then in 1 step. Somehow it's just how they do it, right?
Wait,
Okay, and
to me, it seems like what this tells us is that the encoding is not enough for the model. They still need to use information from the original pixel matrix. If I understood correctly, because the projection compares to the original image, right?
yeah, but you only use the encoding, right? So you basically you give the MLP the encoding and the previous prediction. So the MLP also learns to self-correct, basically.
But the reprojection loss compares
Yes.
the projection with the original image, right?
Yes, but of course, during inference, the model does not know the ground truth. So I don't understand what your question is exactly.
But what I mean is that, so usually in the loss, you compare your estimate with your ground truth. But in this case, the ground truth
Yeah,
using the
that's
loss
true.
is
That's
the
true.
actual image.
So it's again underdetermined, right? You don't actually
Yes.
compare. You have no 3D label you can compare your actual prediction to. You have to basically take your prediction, project it back, so throw away information basically, and then compare this projection to your ground truth.
But not necessarily 3D. What I mean is that you don't project in the embedding space. Or do they?
Yeah, no, you don't. Of course, you don't project your actual parameter vectors. You project
Yeah, okay. Yeah, so what this seems to
something
tell
that's
me.
derived with the SMPL model.
Okay, so what
Yes.
this seems to tell me is that the embedding is not enough because you still reproject back to the original image in your loss. I don't know if that makes sense.
Yeah, I'm not sure if I understand. Yeah, okay, I understand what you mean. I guess so. I'm not 100% sure. Maybe we can talk about it later too.
Right, okay.
Okay. Okay, so this is then so this is optional. So you basically can, if you have, so this is what you would do in practice also, right? If you have some, you can imagine you have a training data set and you have images, but you also have some ground truth images where you basically have mocap or even SMPL parameters, right? So mocap would mean that you have the 3D positions of the joints. You don't have the 2D, right? Then you can just do this. You just basically take the predicted positions of the joints, and you do an L2 loss. And then if you have actual SMPL parameters, so if you basically have some data where already an SMPL model is fitted onto the person through mocap, usually, as I said, somehow, you can then directly compare these parameters again with an L2 loss. So I think this is pretty straightforward. You just basically have, if you have additional information, you can add it to your loss. Okay, and then I don't show this here, but then the overall loss so far will be the reprojection loss plus this 3D loss, which you will give a weight, of course, because you will probably weigh these in some way. So we will weigh these less. Okay. Okay, and then here is the monsters I already showed. So far, if you just use the pipeline like this, you will produce these kinds of things, right? So it's not going to be work exactly. So what they do now is you basically do what they call a factorized adversarial prior. So I already talked about the basic idea. You have some discriminator, right, that takes in the 3D. Not actually the model takes the parameters and compares it to a database of SMPL meshes and says, okay, these parameters look right. They look like a human, or they don't look like a real human, right? And it's trained to do that. Now the actual like part of the trick here is, as you saw, the SMPL model, it's not a black box model at all. It's a very explicit model that is very factorizable, very modular. You have a lot of different components of it. So what you can basically do is you can factorize the latent space. So you can model basically the shape and pose separately, and you can model the joints separately. So what they do in practice is you don't have one discriminator that does the whole thing, just puts out 0 or 1, but instead you have k plus 2 discriminators. So k is the number of joints. So you get one for each joint, and I think one for the root, and I'm not quite sure what exactly the number of k plus 2 comes from. But basically you factorize it in the number of discriminators, which all basically put out 0 or 1, whether or not they think it's human. And then you can basically take the aggregated result like that, right? If they all say it's a human, it's a human. If not, then if one of them says no, it's not. So it's a probability, right? So you will multiply them, of course, then, and have some kind of threshold. So then here, this is just the adversarial loss, and then a discriminator loss. So this is, this is pretty much like in a GAN, I would say. Okay. Any questions for this part? So this year you have
I didn't quite
key data.
understand like how many discriminators in total they have. So
Why it's k plus 2
okay, one for
each
joint.
joint, one for the root, I think, and then one.
Isn't
I
it
don't
just beta
remember.
and theta? The plus 2?
So the problem in the monsters, sorry, Martin, the problem in the monsters is kind of the direction, right? Again, I'm saying the same thing.
Yes.
So maybe that's why they have 3 discriminators. Because maybe the position is correct, maybe the joint is correct.
Yeah, basically you have
How
one
is it?
discriminator that will say, okay, you will have one discriminator to say, okay, does this make sense? One will say, does this make sense? One will say, does this
But
make sense? And
for
so on,
each
right?
joint, you have 3 discriminators, right?
I mean, it's one, I think, in their nomenclature. I guess I understand what you mean, but it's one MLP, right?
No, 1 MLP, but how, why K plus 2 again? Sorry.
As I said, I don't remember the exact how you exactly get
okay.
to this
Okay.
number, but I can after the talk we can look at the paper. I will tell you exactly.
Okay, no problem. Okay,
I
they
don't
have
remember right now.
more than one discriminator. Maybe probably they need more information about the pose, etc. Okay, sorry, Martin, I interrupted you.
No, to me, what it seems like is they use you mentioned you use shape and pose separately. To me, they use
Yes.
like beta or theta,
Yes.
and then they compare it. They compare that one with the joint. And this
Yes.
is what a discriminator takes. It takes the shape, it takes the joint, and it asks if this is plausible.
Yes. Yeah.
Is that it?
Yeah. Yeah, it's true. I understand what you mean. I think you're right. Yes. It's also so. Okay, so I want to give some additional comments. So this whole thing works in part. It works so well because you can factorize this latent space. You get a lot of small discriminators, right? Which are easier to train. They're more stable than if you did the whole thing in one gun, right? Sort of gun model. And then another thing is because you have the reprojection loss, you already have a bias in your gun. So the gun basically you don't have mode collapse in this situation, right? Because the gun has not just the discriminator does not just need to learn discriminating, it also at the same time will be basically you have to optimize the discriminator loss, but also the loss of the reprojection. So you don't really get mode collapse in in a situation like this because of this. So this adversarial prior is actually very stable compared to like a gun or something. Because I mean, you guys know, I don't have to tell you, if you do adversarial trading, usually it can be you can have a lot of problems. So
Yeah, the main
with
one.
mode collapse, or one of the things dominates or something. So you don't really get this problem
So
with this
Aaron,
setup.
this paper is
Yes.
in 2023, right? So you will explain
2018.
18.
Yeah, 18.
Wait,
So
is
it's
it
pretty old.
SMPL still?
What?
This paper is SMPL, right?
No, this is the so this is the where is it? Here, this paper. This is
Okay. So
2018.
when did
So
you finish talking about
SMPL
SMPL?
SMPL is 2016. So this is I
Uh-huh.
finished here after methodology. Yeah, that's true. I should have made clear. So this is actually still now talking about the new paper. The SMPL paper, if you look at it, it just describes how to do work with the SMPL
Okay,
model.
so you said 2016 for SMPL.
SMPL, I think, is 2016, and this paper is 2018.
But
So
the
it's pretty
problem
old.
is it's 2023 paper in Google Scholar. It's weird.
It might be because I was updated at some point.
Probably, yeah, probably. I
But
will
it's
check.
it's an older paper, right?
Yeah. It's, even the shapes, even the figures looks older.
Okay. Okay, so let's look at some of the experimental results. And okay, so let's just start with some qualitative results. So they use two benchmarks. They use human 3.6 million, and then the other one is MPI 3D HP. It's called. So these are like very well-known human pose estimation benchmarks. I don't know if you've heard of them, but I mean, it's not that interesting, right? It's just a benchmark. You have some humans, and then you have some skeleton annotations. So obviously they cannot use they don't use meshes. They use just the skeletons, as I've said. So you have some results here, and these are from percentiles. So basically, the more right you go, the more wrong they were. And you can see that even for 95th percentile, so basically a very high error, these still are pretty good, I would say. So they still make sense. There's some, it doesn't match up exactly. Like, for example, here you can see the legs are not quite right. Or here, this is also not quite the pose that the person is doing, but semantically they are very similar. So it's not that the pose is doing something completely different. It's just that it looks similar, but it's not quite right. Actually, you could imagine if someone was looking at this picture and then they had to do the pose, then they might do something like this, right? And then if you look at the good, like the very high low error ones, these actually look very good. So, for example, here, this is pretty much exactly the pose that the person is doing. So, just qualitatively, the results are pretty good, I would say. Very, very, pretty impressive, I would say. Because, I mean, I don't know how you guys feel about this, but to me, this problem of just taking an image and you have to construct a complete mesh, it seems very almost impossible, kind of.
And that's crazy that they did it like almost 10 years ago. It's unbelievable.
Yeah, right?
Yeah.
I mean, not
And I think
impossible, but very difficult because you're lacking data.
Yeah,
I
not
mean,
impossible, of course. You have, I mean, a human can sort of do it in the
yeah,
brain, but
yeah, that's what
it's a
that's what I
difficult,
wanted to
very
say. We can
difficult
do it, so
problem.
it's not impossible.
Because what's impressive to me is, I mean, as someone who works in pose estimation somehow, even standard pose estimation where you just have a skeleton can be pretty challenging, especially if you have occlusion or stuff like that. But this works pretty well, and you saw in earlier examples that it also works well with occlusion to some extent. So, for example, here, this example, you don't see the legs of the person, but you still get some good leg
yeah.
leg model. Okay. Right. So let's look at the results. So this is on the human 3.6 million. You don't know these data sets, so I don't know how interesting it actually is for you, but I'm just going to talk about these a bit. So you can see here, obviously it's a little bit difficult to compare because there aren't at the time there were not many comparable methods, but they compared to what's called Simplify, which is a similar method that they used. Also, it's from the same people basically. And by the way, this paper, I should also say, this paper is from the same people who also did the SMPL model, right? So it's basically it's an MPI group, MPIIS group from like Michael Black and some other people that introduced the SMPL originally.
Is
I
Michael
don't know
Black
if
the guy that has like 300,000 citations?
yeah. I think
Yeah.
it's actually his most cited paper, one of his most cited papers, the SMPL paper. I don't think he's the main author, but he's definitely on this paper, and he's also on this one, right? So this is sort of related work somehow.
Mhm.
And they compare it here to when you have a star, it means the model gives the full mesh, right? And these only do the 3D joints, right? So obviously you can see here that, for example, this one is better than the HMR, but this makes sense actually because the HMR is not a pure skeleton model; it outputs the whole mesh. So you cannot really, you cannot expect it to outperform a model that is specialized for just producing the pose, right? So it makes sense actually. And then here they actually have HMR, and then HMR unpaired. And what this means is this model was trained with images and then some images with where they have 3D labels, right? And this one is just images. So you can see that you get a very significant boost, but it's still competitive, this model, which was just trained on images. 1 second, I have to take a minute. Okay. So, okay, in a human 3.6 million, you have 2 protocols, so basically 2 kind of evaluations. I don't think it's very interesting for you guys. They also have some other metric. This is a very common metric for human poses. It's called mean per joint position error.
Bro, do they get an error of over 100%? What the hell is this?
I mean, it's not a percentage error, but yes.
Okay.
Okay. Yes, so this is the other data set. Here they have, I don't know why they use different metrics for this. So they have again MPJPE and then PCK, which means percentage of correct key points. And then AUC is it's derived from this. So it's basically, I don't know, maybe you know this from object detection. You have to put a threshold for when a key point is correct. And the AUC is simply you take the curve where you vary the threshold and then you take the area under the curve, right?
Yeah.
I think you know this probably.
Yeah, it's like
This
rough
kind of
sketch.
idea. Yeah, exactly. And then here again, you can see it's very competitive, even with the methods that are only output a skeleton, which is pretty impressive, right? Okay. And then here they do another task. So these 2 were joint locations, right? And then they do another task, body segmentation, where you have basically a segmentation of the body. So different body parts are segmented. And then you can do this with the model too, because you have the basically the blend weights, right? And you can use this to do a body segmentation. So it tells you which vertex belongs to which body part, and you can just use this to a body segmentation, and they can do this, and you can see that it's pretty competitive to the other methods. And what's actually interesting here is that this, you can see here now how fast it is. So this is 0.4 seconds per image. So it's very fast compared to like 1 minute for the simplify. And then here, this one's also pretty fast. I don't know which one this is. Decision Forest, I guess. So it's comparable to this one, but it's real time pretty much, right? 0.4 seconds. 0.04 seconds, I should say. Okay. What is this? Yeah, okay, this is interesting. So this is basically these are some examples for the most sort of basic situation where you don't have any 3D labels, right? So it's unpaired. You basically only get image data. And you can see that these still are very sensible. So some of these, for example, I'm not actually sure what pose this person is doing. But this, I would say, maybe is a bit off. But in general, these look pretty good, I would say. Yeah. So basically, it's just that if you look at the actual error, reconstruction error and stuff like that, you do see a difference for the unpaired model. But in practice, even the unpaired model works pretty good on actual examples. Okay. Any questions so far?
Nope.
Okay, I just have a very short conclusion. So this is basically the first method that works very well for human mesh reconstruction in the wild, so to say. So I think some other method like simplify or something, you could also use this, do this sort of thing before, but this basically works out of the box very well for some images, so it's very robust. It even works well if you have no 3D supervision, so basically just the images, and it works in real time. So it's basically you have many different things in conjunction here that make this very very good results, I would say. I mean, it's not random that this is very influential paper. So it has, I don't know how many citations it has, but it's definitely one of the most cited papers in this field. So yeah, there has been a lot of work that has done this kind of thing with more modern methods. I cannot, I don't know that much about the details. I have not read many papers on this, but there are a lot of similar methods like this. And this kind of thing is, of course, used all over the place in industry, basically. As in industry, in this case, of course, means stuff with virtual humans or like AR stuff, VR stuff, then like animation studios. They use this kind of technology, right? It's basically a kind of alternative to motion capturing. So yeah, I think that's it. Do you have any questions?
Thank you.
Yeah. By the way, I checked on the paper about the K+2 stuff,
Yes.
and what they
Enlighten us.
mean. Yeah, what they mean is indeed what I wanted to say. So you can factor. So they talk about the SMLP.
Yeah, right. Yeah.
Yeah, they talk about, no, it's a bit further above.
Mm-hmm.
It's this paragraph, unlike the previous approach. No, okay, no, the one just above it,
This one.
just above this one.
This one, yeah, I remember
Yeah.
this. Yes.
Yeah. So what they say is that they know the meaning of the Latin space. They can factorize it with beta and theta, and theta itself is dependent on the values of each joint. And so what I said before about the fact that each joint has biological limitation, they want a discriminator for each of these joints to infer these values empirically from the data. So that's why you have K+2. You have a discriminator on what pose is like acceptable. Same for the, what is it? What's the name? The pose and the shape, that's it. And furthermore,
Yes.
they want one for each joint to determine the feasible angle, the range of motion, basically.
Yeah, you're right. Yeah, I think I remember. Yeah. Yeah, I mean, this is really the basically the the upside to if you have a model like this that is super interpretable for this kind of thing. Definitely, that you can basically factorize it explicitly. Okay, I think I'm gonna stop the recording now, unless you guys have something you want on tape.
No, it's fine.
Okay. Thanks, everyone.
Yeah.